Good morning everyone, we are Group 5 and today we'll explore a powerful synergy at the heart of modern manufacturing, simulation and structure analytical tools like the N7 tools. As industry races into the era of Industry 4.0, simulation has become essential for designing smarter, more adaptive manufacturing systems. Alongside it, N7 tools like affinity diagram, interrelationship diagram, and tree diagram offer a semantic lens to analyze problems under root cause.
A tree diagram is one of N7 tools that break down goals, problems, or tasks to be more specific components. It helps to identify the necessary action, causes, or solution that needed to be achieved the objective or resolve a quality issue. In the journal that we researched, they use tree diagram to break down the goals or the effect when using simulation for design and operating of manufacturing system. As the result, it breaks down the goals into actionable components that enable to optimize design and decision making within Industry 4.0 context. It also easily can trace the action to improve the performance. So, as we can see, it has listed out into three objectives, which are simulation as main objective, objective 2 as factor of using simulation, and objective 3 as the causes effect of using simulation. By using this tool, it helped the company to break down the goals and the effect.
The main objective of the simulation was to optimize manual assembly tasks by using virtual simulation to analyze ergonomics, improve workflow efficiency, and ensure worker safety all before physical implementation. The simulation generates cycle time data to analyze how long each task took. It identifies ergonomics constraints, pointing out areas where physical strain could occur. The process enables clear visualization of the operation. Now let's look at this arrow diagram. It maps out each step in the process. Step 1. Set the user parameters by choosing the appropriate simulation setting. Step 2. Start the process to begin the fitting and fixing activity. Step 3. Pick and move the part to the correct position. Step 4. Fix the part into its place as intended. Step 5. Check whether the part is fixed automatically. If it is, skip the fixing step and go straight to the result. If it is not, continue next step. Step 6. Pick and move the required tool or fastener. Step 7. Place the tool or fastener in the proper position. Step 8. Use it to securely fix the part. Step 9. Stop the process once the task is done. And last step is step 10. View the result including the time taken and ergonomics data.
Next, we look into the interrelationship diagram. This diagram illustrates the conceptual framework for integrating computer-aided process planning (CAPP), computer-aided manufacturing (CAM), and computer-aided design (CAD) in a production environment. So, how they connect? The diagram clearly shows the information flow between the CAPP in the blue box, CAM, the green box, and the CAD, the orange. The CAPP feeds into the CAM and CAM generates outputs that link back to CAD, likely for simulation or verifications. Now we look at each breakdown flows. The process 1 identify manufacturing process and machines. How is the CAM receive information from the CAPP? The second process identifies setups and features, get operation sequence, and machine switches as the CAM's role in translating process plan into the specific manufacturing instruction. The third process is getting cutting tools and cutting parameters. It's utilizing the information from CAPP for machinings. The fourth process generate the cutting parts, CNC code, and simulation. The core function of CAM, producing the actual machine instructions and allowing for virtual testing. Lastly, the process number 5 is the role of CAD that's worked as input for CAPP or CAM while not explicitly shown as an input to CAP initially. CAD models are the fundamental basis for all subsequent operations. The errors from CAM simulation back to CAD suggest a feedback loop for verification, design refinement, or further analysis based on the manufacturing simulation results. Next, we are moving to the objective of this diagram. This diagram occurs to transform design ideas into physical components in an economical and competitive manner. The integration workflow of these three components enhance manufacturing efficiency back from a closed-loop system for optimizing manufacturing process. It is also the emergence of the intelligent CAPP system in manufacturing that involve advanced, flexible, and environmentally friendly approach. This diagram shows the data exchange that enables better decision making that is proven by the CAM that provide cutting tools, parameters and machine setup for CAPP for refining the process, and it allows continuous optimizations based on CAM, simulation or production data. This interrelation also supports customization and flexibility of production environment and the digital automation that's a proof that improve productivity to accelerate production planning execution.
Today, I will be presenting the discussion and finding from our group topic. First, let's look at the tree diagram. This diagram breaks down the entire field of simulation in manufacturing into 7 key domains. For example, it includes tools like CAD, CAM, and CAPP under CAX technology. This classification helps us understand where and how different simulation tools are used, whether it is in design factory layout, simulating material flow, or managing production network. The arrow diagram presents a timeline that tracks the evolution of simulation technology from as early as 1777 up to present day. It highlights major shifts like a move from analog to digital simulation, and more recently, the integration of Industry 4.0 technologies such as a twin, digital twin, and hybrid simulation. This shows how simulation has advanced alongside technology. Next, the interrelationship diagram shows how different simulation tools and technologies connect and support one another. For example, we see how CAD, CAM, and CAPP systems integrate to improve process planning, or how augmented reality, MES, and SCADA systems work together in the real-time environment. This visualization proves that simulation is no longer a standalone tool, but part of an interconnected digital ecosystem. One key finding is that simulation is now used across the entire product and production lifecycle, from design and planning to layout, material flow, and ergonomic. Simulation support manufacturer in making better, faster, and more cost-effective decisions. The second major finding is the role of emerging technology. Augmented reality and virtual reality are helping simulate workplace and design in a more immersive way. Digital twins combine real-time data with virtual modeling for real-time decision-making. Hybrid simulation help module both continuous and discrete system effectively. Despite this advance, integration remains a challenge. Many simulation tools still struggle with interoperability. Systems like SCADA and MES need to harmonize data better, and there are a growing need for standardized across platforms. Another significant finding is a gap between academic research and real-world industry practice. While research has introduced advanced simulation concepts and tools, many industries are slow to adopt them due to complexity, cost, or lack of technical skill. Bridging this gap requires making tools more user-friendly, investing in training, and fostering better collaboration between university and industry players. Looking ahead, the vision of the virtual factory is becoming a reality. This means we will have a full digital mirror of physical factory. Using real-time data, manufacturer can simulate everything from predictive maintenance to energy usage before it happens. This reduces downtime and accelerates product delivery. Thank you for your attention. This concludes my part of the presentation.
The conclusion of this research, we can say that simulation is not just a tool, but a transformative enabler in the design and operating of manufacturing system, especially when combined with unstable problem-solving tools and Industry 4.0 technologies like digital twins, Internet of Things, IoT, and AR, VR. It empowers manufacturers to optimize decision-making throughout the entire life cycle of manufacturing system, transforming how industry design, operate, and improve in an increasingly complex and digitalized world. So that's all from us. Thank you.